Hello, this is an example to show the optimal design for a pipe irrigation system where water is taken from a source at an elevation 500 foot and pumped through two pumps into 10 pipes to reach the 5 terminal nodes for irrigation purposes. The nodes are 5, 6, 7, 9, and 8. We are going to try different types of designing the network. But before go to optimal design or design, we have to look at the system layout, constraints, and costs. Flow at the terminal nodes are 4 cubic feet per second each. Velocity should not be larger than 6 foot per second, and the terminal head nodes should be greater than 580 foot. The system cost is chosen to be linear, where we multiply a constant by the pipe diameter to find the cost of pipes, and multiply a constant by the horsepower to find the cost of the pump. We try here a trial and error method of design by dividing the spreadsheet into sections, one for input data to define the pipe friction factor, the water source elevation, the minimum terminal elevation, and the maximum velocity, which is 6 foot per second. Then we had a section here to calculate the terminal node pressure, starting from the source and going through the two pumps until we reach the nodes 5, 6, 7, 9, and 10. And a section here for the design calculations for pipes, including pipe number, diameter, length, discharge. The discharge is calculated backwards from the 4 CFS at the terminal nodes, the head loss, and the cost of pipes. The cost of pumps are shown here, but because pipe diameters and pump heads cannot be continuous variables, we have to choose the values for cost of pipes and pumps from a table here, where these are the available diameters in the market and the available pump heads in the market with the corresponding cost coefficient. Because this is a trial and error, we can change the diameter here. Say if you put this 20, we'll find that the velocity is exceeded because we reduced the diameter. If we do the same thing for the first 3 pipes, we found that not only the velocity constraints are violated here, but also the constraints on the terminal node. And we keep changing the diameters. We started with a feasible solution, but you can, of course, if you try different diameters, you'll find that things will get, we used the conditional formatting in Excel to show the violated constraints in different color to allow or to facilitate the design or the finding of a feasible solution. Here we put this 18. Here, the total cost is 55,000 monitor units, and this is a solution with a trial and error. But we can find an optimal solution using the nonlinear optimization program in Solver by going here and we try a starting point, like say, for example, the same starting point that I used in the previous slide. That is infeasible. It's a starting point. Then we put ourselves for the total cost and go for data solver to show that for this particular total cost cell, we like to minimize it by changing the variables. In this particular case, I changed the diameters only, subject to 2 constraints. One of them for the nodal head constraints, and the other one is for velocity of through pipes. Then I use the GRG nonlinear and push solve to find a solver solution. Now, this is the solution we obtained. I will keep the solution. We notice that the total cost here is decreased. Why? Because we used continuous values for diameters, which of very little practical value, because diameters has to be chosen from the table of available diameters here. If we like to round these continuous diameters, we obtain a discrete value for diameters by choosing from the table. And it was just an accident that the same diameters we chose for discretization are the same we obtained for the trial and error method, and therefore we come up with the same total cost of 55,000. Velocity constraints are satisfied and nodal head constraints are satisfied. For some larger problems, and for very good reason, because obtained nonlinear solution is not guaranteed to be a global minimum, we used a linear model. This linear model transforms the original formulation from a nonlinear problem to a linear problem by expressing the head loss equation in terms of candidate pipe lengths, where the S here with the slope of the friction line is expressed as 8F Q squared over pi squared multiplied by GD to the power 5. And this substitution will replace the nonlinear diameters with linear lengths of pipes. To show you how this is done through the total energy line, this is the original pipe here with length 3,000 foot. And then we divide it into 3 lengths, candidate lengths, but we choose the diameters for the 3 lengths. And these diameters has to be chosen to satisfy the velocity constraints. Therefore, the unknown D's are replaced by 3 known diameters, D1, D2, D3, and the known L is replaced by 3 segments, L1, L2, L3, which is still unknowns. Then we go into the linear model. The number of variables will not be 10, but will be 10 by 3, because each pipe is replaced by 3 candidate lengths. Therefore, we have 30 variables. For pipe 1, we have chosen candidate diameters to be 27, 24, 21. And then here, this is the optimal solution. But just for the sake of demonstration, I will assume that this segment is 1,000 foot, and then put it 1,000 for all the segments to satisfy the total length constraint. Then go to data, solver. We place ourselves as the total cost. Here, we like to minimize the total cost, and the variables here this time are the pipe lengths and the head of pumps, subject to the 2 constraints we used before, one for nodal heads, and the other one, we don't need a velocity constraint because the choice of candidate diameter satisfies these constraints automatically. But we add another constraint to make sure that the sum of the candidate lengths or the pipe segments has to be equal to 3,000 foot. The same thing, we put some limits for pumps. Here we don't use GRG nonlinear, but we use a simplex LP, and then we solve. Then we got the same solution we showed before. We like to notice here that as a result of this linear model, not all pipes are divided in 3 segments. Only 3 pipes are divided into 2 segments, and the 7 remaining pipes have only 1 segment of length 3,000 foot. Here, we try to compare or summarize the different computational exercises we showed you. The trial and error method, the infeasible one was costing 49,000. When we used the nonlinear optimization, we got a feasible optimal solution of cost 51,057. But this solution is of little practical values because the values of diameters and pumps are not discrete. After discretization, we arrive to a feasible discrete solution, but the cost, of course, increased. When we use the linear model, we obtained an optimal solution, global optimal solution, and the cost is even less than the optimal discrete solution and has a value of 54,143 monitor units.